is not greater than or equal to 0, this function is not real. So restrictions. So the domain will be given by this, right? Domain for this function is 1 to infinity. Can anyone think of another function? Because this function will join this group. If you want, it's an elite group, but can anyone give us another example of a function in which we have to worry about the domain? What about 1 over x plus 2? How will I write the domain of such a function? What is the condition that will give us the restriction? Here, this was the condition. The quantity underneath the square root has to be greater than or equal to 0. What is the condition here that I have to write?
X cannot equal 2 or negative 2.
Indeed. X plus 2 cannot equal 0, which means x cannot equal negative 2. The domain for this function is negative infinity, negative 2 with a parenthesis, union, parenthesis again, negative 2 to infinity, to exclude negative 2. Awesome. So now we need to know that log, and remember that log is a problem, or potentially have a problem, and it joins the even index, any even index here, and rational functions, because not always, but we always have to think and worry about this, what the quantity under the square root, and we always have to worry about the denominator of a fraction like this, of a rational function, or other combinations of functions. But these are two examples. Good. Next step. The log functions notations, first of all, notation. It's a fancy notation. It doesn't mean anything. It's just a way of identifying the log. So we're going to use log. Towards the bottom of the loop of G, we're going to put a base. Can be A, can be B, can be anything. And this is the independent variable. How do we read this? Log base B of x. Log base B of x. B has exactly the same characteristics that the base A, I wrote it here A, doesn't matter, it can be B, either greater than 1 or between 0 and 1. Otherwise, it would not be the inverse of the exponential, right? So B can be either greater than 1 or tiny between 0 and 1. It cannot be 1, it cannot be 0, it cannot be negative. Now, we do have two special exponential functions, and we have two special inverse functions for those. Okay, special exponential functions and their corresponding log functions. We have two, and I'm going to show them where they are in the calculator in a second. So as we know, f of x equals 10 to the x. It's an exponential function with base 10. It's called common exponential function. Of course, it has a correspondent. So the f of x, that is the inverse function of that, is denoted by log x. And you can say, what is your base? By convention, we do not write it the base 10, but you know it's there. So every time you do not see a base, you have to think that it's 10. I'm going to share my screen for a second just to show you that they share the same key in the graphing calculator, right here. See, the exponential function is activated with the second key. Here it is, 10 to the x, but log is right there. You just click on log, put 7, and that means log base 10 of 7. You click enter and you get the answer. Good. The next one is f of x equals e to the x. It's natural exponential function. And naturally, it has its correspondent, f inverse. Remember, this notation is not 1 over f, but it's f inverse, is ln natural log of x. So I forgot to mention that this is the common log function, and this is the natural log function, right? Common log and natural log. Of course, when you see something like this, you know the base has to be e. They will not be inverses of each other if they did not have the same base. So if this is base e, this is automatically base e. We don't write it. I'm sharing my screen so that you can see they share the same key right here. They're inverses of each other. With the second key, second option, you have e to the x and natural log of 8, for example, and we get whatever. Okay, so we know that. Moving on. So I like to look at something like, and I did print out from your professor sent me this. So we already did this, but I really like the fact that I was able to print this out and show you again how we graph something like this. From the very beginning, these graphs are a picture from of the graphing calculator or with a computer algebra system. However, I want you to understand that this graph will not at -5 overlap with the x-axis. Please understand that that is maybe the error of the computer or the error of the software or the calculator. No. Okay, so this is very confusing, although you do see the points. So it's a very good graph, but I want you to be very skeptical and say, oh, no, 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 I know it's very difficult to graph. They will not, these two, the x-axis and the graph, will not eventually overlap. Okay, definitely not at -5. So be careful with that. So if we want to graph the log function, I will always have to graph, as I mentioned before, the line y equals x. So if you decide to print this page out, it's awesome. So this is y equals x. We are going to reverse the points that we see with respect to y equals x. This is our mirror, and we will create a mirror image like we just did. So this point moves here, and so on and so forth, and all we need to do is just graph. Yes, we'll reverse all the points, but I don't want to spend too much time on this because we already did it. So if this is 3 to the x, this is log base 3 of x. Increasing, increasing, base greater than 1, which is 3 here in this case. And they are again a mirror image. So if you fold with respect to y equals x, they have to overlap. Good. I just wanted to show. I'm gonna put this in with your notes. Okay. Next thing I would like us to look at transformations. When you graphed, for example, f of x equals e to x plus 1, you initially graphed e to the x. Can anyone refresh our memory on what does this do? So when x is basically changed into x plus 1, which transformation will this be? Anyone?
Move to the left one.
Excellent, brilliant. So this point, this is my landmark, moves here. And then I graph. Using transformations, no one is asking us to graph exact. So if this is the graph of e to the x, very good. This is the graph of e to x plus 1. We want to do the same thing. We want to look at an example with transformations on the log function. Would you prefer a log function with a base greater than 1 or less than 1? If you'd like to make one up, please make one up. If you don't want to make one up, we can choose. I'm sharing my screen right now. We can choose. No, that's not what I want. I want it here. But if you want to make one up, you can make one up. Okay, so it says use transformations of the graph. So this is on page, I have no clue, 490, okay. On page 490, if you'd like to choose any example so we can work on transformations, feel free to choose, or simply make one up. So we can illustrate transformations with log functions. Anyone? Okay, I will choose 62. 62, we have age of x, log x minus 2. Oh, sorry, I didn't see the chat. Ah, good, awesome. Very good. Thank you. So first thing, we have to identify these, my props come in handy. We have to identify the base function. What function was used for this function? Well, obviously log x. So this is common log. Common log is a function that is increasing on all its domain, or it's decreasing on all its domain, and how do we know? It's okay if you're wrong. Just tell me your idea. What do you think from what we discussed so far? Will it be any... Say that
From the
again?
negative infinity, it's increasing.
It's
to the-
increasing because the base is greater than 1. Because the base is greater than 1, the function is increasing. And we know pretty much this is the shape. So this is log x. Perfect. Now, what transformation is this on log x? Again, it's okay if you're wrong, just say what you think so we can correct it. Or say, yeah, that's great.
Move to the out or down.
Excellent. Very good. So this was a little bit tricky, right? Because if I put parentheses, then we move the graph to the right too. But we don't have parentheses. If you want, you can put parentheses just to be very clear and specify. So this is definitely a transformation on y, right? So it shifts down 2. Good. So here's my landmark. I go down 2. That's the point right here. Of course, I didn't perform any calculations. We don't know how to do those yet. We will. So this is log x, and then outside minus 2. Now, since we are here, how will you write the domain of this function? Let me refresh your memory a second ago, and maybe 10 minutes ago. We talked about the fact that log is defined only on positive values. So I look at log, it's applied to x, and then outside minus 2, nobody gets bothered by that, whatever. So what will I write in order to find the domain of this function? What should I write? It's okay if you're wrong.
0 to infinity.
Excellent. So I will write, because log is applied to x, I will write x greater than 0. This is the restriction or the condition that will give us the domain as 0 to infinity. Awesome. And that brings us to finding some more domain. And then more interesting stuff about log function. I'm on page 4. Okay. So I'm sharing my screen, so let's take a look. We want to look here at any of these problems from 75 to 80. 75 to 80 on page 490. Find the domain of each log function. So please look and pick. If you don't pick, I will. Anyone? Okay, I have a chat. 77, awesome. Okay, so we have 77. Thank you for picking. F of x equals common log in parentheses 2 minus x. Awesome. So the problem is asking us to find domain. What do I have to write? What is the condition that I have to write and then solve and then find the domain? What will you tell us to write? By comparison, look what we did here and what we wrote. So what would you tell me to write for this one? Again, it's okay if you're wrong.
Is it moving up 2x?
No, we're not graphing. Do not graph. We are only interested to find the domain. Let me refresh your memory before you say anything else. For such a function, we wrote that this quantity had to be greater than or equal to 0 for the function to be real. For this function, we wrote that the denominator cannot be 0 for this function to exist. Similarly, we have to write something for this function. What will I write? Only if you tell me what you think, I can correct it. And that's fine.
Is that a function? Because 2 first and then minus x.
No, at the moment I use parentheses, it's carved in stone. Log is applied to 2 minus x. So the previous situation had parentheses around x. And we wrote that this quantity has to be greater than 0. What will I write now for this?
Greater than 2?
You're saying 2 minus x greater than 0. So now this time this piece has to be positive. Is that what you meant? Yes? Do we have any questions? Do we understand this step? No, very good question. It cannot equal 2. Look at the graph. Let's look at the graph. When x is 0, this function goes to negative infinity. You cannot plug in 0 in this function. When x is 0, this function is going to positive infinity. You cannot plug in 0. In the square root, I can, as long as it's not in the denominator though. So I can plug in 1 here. But we cannot plug in 2 here because 2 minus 2 will be 0. Log of 0 is undefined. It does not exist. There is a D in here. Sorry, I always run out of room. In case you have any doubts, you can always go back and say, how come? Okay, and just plug in any log you want. Log, okay, plug in 0. The calculator will scream at me. Let's see the calculator scream. It's screaming. So please remember, log cannot be applied to 0. So therefore, I cannot have the equal symbol here. So negative x, move 2 to the other side. When I move a term from one side to the other, all I need to do is change its sign. How do we solve this? What do I have to do to both sides to solve this inequality?
Divide by -1.
Okay, so then I have 2. What happens with the inequality symbol when I divide both sides by -1?
It flips.
Awesome. So can anyone tell us the domain of this function now?
-infinity to 2.
Brilliant. Thank you so much. Awesome. Thank you very much. Great. I think we need one more quickly so we can move on.